Section 2.1 presents two applications of limits. In the last class, we saw that a limit can be used to find the slope of a tangent line. Today, we will use a limit to find the instantaneous velocity of a moving object. Take a review about what we learned in the last class. Review number 1. Suppose we have a line and suppose we want to find the slope of the line. To find the slope, we arbitrarily pick 2 points on the line. Then the slope formula is y2 minus y1 over x2 minus x1. Review number 2. Suppose we have a line and suppose we load 1 point on the line and also the slope of the line. Then the equation of this line is y minus y1 is equal to slope parenthesis x minus x1 parenthesis. In this equation, y and x are variables. y1 and x1 are the coordinates of the point P. They are constants. Review number 3. Suppose this curve is the graph of some function f. Point P is a point on the graph. At the point P, there is a tangent line, and suppose we want to find the slope of this tangent line. About this tangent line, we load only 1 point. On it, we load only point P. We don't know any other point on the tangent line, so we cannot use the slope formula to tell the slope of this tangent line. This is the difficulty of finding the slope of a tangent line. We load only 1 point on the tangent line. We cannot use the slope formula. To overcome this difficulty, on the graph, we arbitrarily pick a point Q. Then join P and Q with a line. About this line, we can write down the slope by slope formula because we have 2 points on this line, point P and point Q. So the slope of the line PQ by slope formula is y2 minus y1 over x2 minus x1. We have this equation. Okay, now we use a limit to find the slope of the tangent line. We let x approach A. When x approach A, point Q will approach point P. Therefore, the line PQ will approach the tangent line. So the slope of the line PQ approaches the slope of the tangent line. In other words, the slope of the tangent line, here M means slope, T means tangent line. The slope of the tangent line is the limit of the slope of the line PQ as x approaches the point A. We load MPQ here. So we plug in this guy in MPQ to get this limit. So to compute the slope of the tangent line, we just need to compute this limit. To compute this limit, we can use a table or we can use any method in the following sections. Now, I present today's topic, find the instantaneous velocity of a moving object. Before I present the topic, let me ask you this question as a motivation. A car traveled 10 miles from 1:13 p.m. to 1:21 p.m. The question is, what is the velocity of the car in this time period? From 1:13 p.m. to 1:21 p.m., the time elapsed is 8 minutes. The car traveled 10 miles in 8 minutes. How fast the car was traveling? How to compute the velocity? The formula to compute the velocity is the distance traveled over the time elapsed. Distance traveled is 10 miles. Time elapsed is 8 minutes. So this is the velocity of the car in that time period. Miles per minute is not a standard unit for a car. The standard units for a car is miles per hour. So let me translate these units into miles per hour. 8 minutes is 8 over 60, so many hours. Now I bring 60 to the top to get this equation. Then by calculator, I get 70 miles per hour. Please note that 70 miles per hour is not the instantaneous velocity of the car. Then how people call this velocity? People call this velocity an average velocity. Precisely 70 miles per hour is the average velocity of the car on this time period or in this time period. This formula is a formula to compute average velocity, not the formula to compute instantaneous velocity. Then how to compute instantaneous velocity? Take a look at this example. A car is moving in a straight line, say on a straight road. Suppose the position measured in meters of the car from the origin is given by this equation, where t is time measured in seconds. On the road, let me pick a point as the origin. Say pick this point as the origin. Then when time, for example, is 0, when time is 0, plug in 0 in t, then we get the position of the car is 1 meter from the origin. When time is 1, plug in 1 in t, then we get the position of the car is 3 meters from the origin. When time is 2, the position of the car is 11 meters from the origin. Now we have some questions. Question A. What are the average velocities for the following time intervals? The average velocity formula is here. Distance traveled over time elapsed. Say, in the time interval from 1 to 2, the time elapsed is 1 second. It is the right end point of the interval minus the left end point of the interval. 2 minus 1. This is the time elapsed from 1 to 2. How to determine the distance traveled in this time interval? It is the position of the car at 2, s of 2, minus the position of the car at 1, s of 1. This difference is the distance traveled by the car in this time interval. Function value at 2 is 11. Function value at 1 is 3. So 11 minus 3, 8 meters. So in this time interval, the car has traveled 8 meters. Therefore, the average velocity over this time interval is 8. Distance traveled over time elapsed, it is 1. So the answer is 8 meters per second. You can say that the instantaneous velocity at any time between 1 and 2 roughly is 8 meters per second. Similarly, the average velocity for the time interval from 1 to 1.5 is distance traveled in the time interval over the time elapsed in the time interval. The time elapsed is 1.5 minus 1, 0.5. From 1 to 1.5, the time elapsed is 0.5 seconds. Now, to determine the distance traveled in the time interval, we compute the position of the car at 1.5. Compute the position of the car at 1, then make a difference. The difference is the distance traveled by the car in this time interval. Then calculator, we get the average velocity over this time interval is 5.75 meters per second. Roughly, you can say that between 1 and 1.5, the instantaneous velocity is about 5.75. We compute the average velocity for the time interval from 1 to 1.1 in a similar way. The answer is 4.31. Roughly, you can say that between 1 and 1.1, the instantaneous velocity at any time is roughly 4.31 meters per second. Question B. What is the velocity of the car at the time t is 1? This question is asking for instantaneous velocity. For instantaneous velocity, we cannot use the formula for average velocity to compute it. Then, how to find the instantaneous velocity in this question B? Let's move on to the next page for the answer. Question B is to find the instantaneous velocity at the time is 1. The formula for average velocity doesn't work for instantaneous velocity. Why? It is because we are dealing with a single instant of time. The time elapsed is 0 and the distance traveled is also 0. If you use the average velocity formula to compute instantaneous velocity, then you will get 0 over 0. What is 0 over 0? We don't know. It is not computable, not computable. Then some people may say that low instantaneous velocity at the time 1, but it is impossible. There is an instantaneous velocity at the time 1. Okay, the average velocity formula doesn't work, doesn't mean low instantaneous velocity. To find the instantaneous velocity, we need to try some other method. In the following, we use average velocity to approximate instantaneous velocity. And also we use a limit to find instantaneous velocity. From part A, we saw that the average velocity over the time interval from 1 to 2 is 8 meters per second. We can use this number to guess the instantaneous velocity at the time t is 1. So we guess v of 1 instantaneous velocity at time is 1 roughly is 8. Again, from the same part, the average velocity over the interval from 1 to 1.5 is 5.75. So we guess v of 1 roughly is 5.75. Now, this guess is better than this guess. This guess is closer to v of 1 because this interval is closer to 1 than this interval. From the third average velocity in part A, we have the average velocity over the interval from 1 to 1.1 is 4.31. So we guess v of 1 is 4.31. This guess is better than this guess because this interval is closer to 1 than this interval is. We continue to shrink the time interval and make the following table. In this table, the first column is for time interval. When the time interval is 1 to 2, average velocity is 8. When the time interval is 1 to 1.5, average velocity is 5.75. When the time interval is 1 to 1.1, this is the average velocity. And when the time interval is 1 to 1.01, average velocity is this. Now, from this table, we can see that as we shrink the time interval to the point 1, average velocity is approaching the number 4. The number 4 is the velocity of the car at the time 1. So we conclude that instantaneous velocity of the car at time t is 1 is 4 meters per second. Part C. Sketch the graph of the precision function. Here the blue curve is the graph of the precision function. Please note that this graph is not the moving path of the car. The car travels forward and backward in a straight line. Question D. So that an average velocity is the slope of a secant line. Each average velocity in part A is the slope of a secant line to the graph of the precision function S. Let's pick the average velocity on this time interval 1 to 1.5 as an example. Here the blue curve is the graph of the precision function S. Suppose 1 is here, 1.5 is here. Corresponding to 1 is the point P on the graph. and corresponding to 1.5 is the point Q on the graph. Because P and Q, they are on the graph of the function, so their y coordinates are function values. Now, join P and Q with a line. This line is a secant line, not a tangent line. By the slope formula, we can write down the slope of the line PQ. It is y2 minus y1 over x2 minus x1. So the slope of the line PQ is this quotient. The numerator of this quotient is the distance traveled by the car over this time interval, right? Position of the car at 1.5 minus position of the car at 1. This is the distance traveled by the car over this time interval. The denominator of this quotient is 1.5 minus 1 time elapsed over this time interval. So this is the average velocity of the car over this time interval. Therefore, the slope of the secant line PQ is the average velocity over this time interval. Question E. So that the instantaneous velocity v of 1 is the slope of a tangent line. Look at this diagram. The blue curve is the graph of the position function S. Suppose 1 is here, and point P is the point on the graph corresponding to 1. Now, on the graph, we pick a point Q, and join P and Q with a line. By the slope formula, the slope of this line is y2 minus y1 over x2 minus x1. This is y2, y1, x2, x1. S of t is the position of the car at the time t. S of 1 is position of the car at the time 1. Position at t minus position at 1 is the distance traveled by the car over this time interval. T minus 1 is the time elapsed over this time interval. So this is the average velocity on this time interval. In other words, the slope of this secant line is the average velocity on the time interval from 1 to t. Now, we let t approach the point 1. T approach the point 1. Then the secant line PQ will approach this tangent line, the tangent line at the point P. As a result, the slope of the secant line PQ will approach the slope of this tangent line. In other words, slope of the tangent line is equal to the limit of slope of the line PQ as t approaches 1. But slope of the line PQ is average velocity over this time interval. So we have this equation. From part B, average, the limit of average velocity is instantaneous velocity. So therefore, the instantaneous velocity at the time 1 is the slope of the tangent line at the point P, at this point. The last question, question F. find the instantaneous velocity of the car at the time t is 2. Similar to part B, here I use average velocities together with a limit to tell v of 2, the instantaneous velocity of the car at the time t is 2. Look at this table. In this table, I compute average velocities over these time intervals. These time intervals are shrinking to the point 2. On the time interval from 2 to 3, the average velocity is 20. So we can say that instantaneous velocity at 2 roughly is 20. On this time interval 2 to 2.5, average velocity is 16.25. Now we can guess instantaneous velocity at 2 roughly is 16.25. 16.25 is a better guess about v of 2 than 20 because this time interval is closer to 2 than this time interval is. Now from this table, we can see that as the time interval is shrinking to the point 2, average velocity is approaching the number 13. The number 13 is v of 2, instantaneous velocity of the car at the time 2.